All right, let's get started. Is this lighting scheme good? Can you see the screen well? Yes? Okay, good. We'll stick with this for now. Although it's a bit dark for me, but that's okay, I guess. As long as you can see it. I don't need to see it. Okay. Now that we've covered a lot of exciting topics in the course, we're going to jump into even more exciting things. More modern microprocessors. What we're going to talk about is not even modern, but we're going to talk about a bunch of design principles today. But before I start, very quickly, how is everything going? How are the labs? Are they good? Are they excellent? Yes? Okay, good. Good, I like that spirit. You're not going to be able to implement a lot of the things we're going to discuss from now on in the labs. But if you take an architecture course later on, you will actually implement some of these advanced concepts. Not all of them, because there's a lot, actually, that goes into the design of a modern processor today. But you will get a good sampling of it in this course, and then you can continue with an architecture course afterwards. But, and everything else is fine also in the course? You guys all know about single-cycle architectures very well now? And the MIPS? Okay, I heard. May not sound good, but we'll cover some of that single-cycle today also. Okay, if this works, we will cover, but of course it doesn't work if you don't have the connecting device on the other side, right? You need to have a receiver and a sender. It doesn't work if you keep sending. Okay, so this is kind of the agenda I have, and this is subject to change, but you've covered single-cycle microarchitecture so far. Today we're going to go into multi-cycle, and probably we're going to spend 2 lectures on this in combination with pipelining. And then we'll talk about some issues in pipelining, like data and control dependencies. Depends on what we're going to cover next. We may or may not discuss state maintenance. We'll cover out-of-order execution, issues in there, and then some other alternative execution models, which are actually interesting. I'll give you a very little aside anecdote that I find amusing today, especially because I don't know, how many of you have heard about Google's Tensor processing unit? Yes? Okay. That's a reasonable chunk. This is basically the new processing unit that Google announced that accelerates machine learning tasks, in particular deep learning tasks, inference that you do. Basically, you train the neural network, and then you put inputs to it, and the neural network tells you this image is a cat, right? Most of the time it's wrong, probably, but that's okay. We're getting there slowly. But basically, they've designed this chip that accelerates this neural network that's already trained. This task is called inference in neural networks. And Google designed this particular chip because they found that doing this in regular processors is a lot of overhead. And I believe their performance results show that you get about 15 to 30x, 30 times speed up if you use this chip to actually do the machine learning inference on the chip. I think this is pretty cool, first of all, because people are designing specialized hardware to do this sort of acceleration for important workloads. Hence, this course is really important. But there's another thing that's really important, which is not on the slide, but it's going to come later on. If you look at the design of this chip, it looks like a systolic array. How many of you have heard of systolic array processors? Probably fewer people. That's good. Because you haven't taken my course in the past, right? So I teach systolic arrays in my architecture course, and we're going to talk about some of those alternative execution models, which is down the line over here. And this is exactly why we talk about those alternative execution models. Because there is no single type of processing model that's good for everything in the world. Sometimes you want to design a systolic array, which you don't know what it is, but you will, a little bit, because that's the best kind of hardware to do the task. The von Neumann architecture, which we will talk about, which you have been seeing, the MIPS processor is not necessarily the best processor to do machine learning inference. That's why the smart engineers at Google designed a systolic array and they didn't use the MIPS architecture. That's why it's important to cover these different execution models in a fundamental way. So whenever you think about them, don't think that, oh, nobody's implementing it today. Why are we covering it? Well, when I was teaching systolic arrays in the undergraduate course at Carnegie Mellon, again, nobody was really using systolic arrays in 2009. But voila, in 2017, people are using systolic arrays, right? So there's a time for everything. So I would suggest learning the fundamentals of how processing is done. And then the job of an architect, as we briefly talked about it very early on, is to figure out how to use those bag of tricks, if you will, when you really need them. Right? So if you went to Google and designed a multi-core processor to accelerate their machine learning tasks, they would have kicked you out probably. But something else could have worked. Okay. Anyway, this is motivation for what else comes after this, basically. We'll talk about systolic arrays, VLIW architectures, GPUs, ... And I don't want to derail the course with systolic arrays right now, because it's a fascinating topic, but we'll talk more. Okay, I'll give you a bunch of readings. This is readings for today, and I'd like you to read from different sources, because different sources covered things in different ways. This is Pat and Patel book, chapter 4, Microarchitecture. Please read that. Actually, chapter 5 also. I think it's chapter 4 and 5. You tell me. If it's not 5, we'll fix that. Okay, and Pat and Patel revised Appendix C is actually really important, because hopefully we'll get a chance to cover the microarchitecture of a micro-coded design. And Appendix A will be useful in following that. And Harris and Harris chapter 7.4 covers the multi-cycle architectures. And keep reading this book, basically. Some of the lectures will follow this book, but we will diverge because no one really covers some of the topics that we're going to cover in the future. And this is an optional reading. Hopefully we'll get to it today, if not tomorrow. You can see that this is from 1951. It's a very bold title, right? The best way to design an automatic calculating machine. It's referring to a multi-cycle micro-coded architecture. Clearly, we have better ways today, but at that time, Morris Wilks, who's a pioneer in computer architecture, has put that name. Okay. Let's start. I'll take a step back, because I think I'd like to introduce the future architectures in a little bit different way. Basically, what we're trying to do is implementing the ISA. We've covered the ISA. ISA is the hardware-software interface. Microarchitecture is an implementation of it. But basically, we would like to take an instruction in the instruction set architecture and process it, right? What does it mean to process an instruction? Even this is dependent on your definition in the ISA, right? So we will assume the von Neumann model, at least for now, but I'm going to stretch your mind a little bit, because again, you're learning the fundamentals. You don't know what the future will be in 20 years, right? Can anybody tell me what von Neumann model is? What's the prime thing in the von Neumann model? Yes? Okay, that's good. That's one property. I'll call that the stored program computer. Basically, you store the program in the same place you store the data, and the way you treat them is different based on when you're actually processing them. There's one more. Yes?
There's memory and there's a computing part. Like, it's not all done in the same step, like, for example, in neural networks where memory and computing is kind of
together? Yeah, that's right, but that's not how it was defined. Sure, you could basically infer that from the basic properties. But I'm looking for two key properties. One is the stored program computer. The other is actually that has been the dominant thing for a long time. And I was expecting, actually, one of you would blurt it out, because it just comes to people's minds right away. Step by step. Sequential instruction processing, right? Basically, everything is sequential in the von Neumann model. There is really no parallelism. You process this instruction first, and then the next instruction, and the next instruction, and the next instruction. In fact, this has been the hallmark of the von Neumann model that has been, in my opinion, ultra useful for people to program because they can think in these steps clearly, right? There is no parallelism going on. Now, in this course, you're getting used to parallelism by implementing stuff in an FPGA, right? You see control signals happening, data processing happening everywhere in the FPGA. It's very different from the von Neumann model in that sense. But von Neumann model, I'll talk about this a little bit. Basically, you basically have an architectural or programmable visible state before an instruction is processed. And then you input that and you process the instruction. This could be an add, right? Add 2 registers, store the result in a register. Inputs are 2 registers, part of the architectural state before the instruction is processed. And the output is architectural state prime, the programmer visible state after that instruction is processed, which is the destination register and everything else, and the program counter. Don't forget the program counter. That's also part of the architectural state. And program counter in the von Neumann model, if you have this kind of instruction, an operate instruction, not a J-type instruction, not a branch, program counter is implicitly incremented, right? You increment the program counter by 4 in MIPS. Well, the reason is it's implicitly assuming sequential processing, right? Basically, processing an instruction means you transform the architectural state to architectural state prime according to the specification of the instruction in the ISA. Now let's go into von Neumann a little bit because I want to make sure that you guys get this one for sure. Basically, it's also called the stored program computer. 2 key properties, as we just discussed. The stored program itself. Basically, you have instructions stored in a linear memory array, just like MIPS, right? Memory is unified between instructions and data, and the interpretation of a stored value depends on the control signals, right? Whether you interpret a memory location, a value stored in an address as an instruction or data depends on the control signals. So when do you interpret a value in the memory as an instruction? This depends on your control logic clearly, right? When you fetch the instruction, if you're in the fetch state of the instruction processing cycle and you're accessing memory, that means that you should interpret that value in that address as an instruction, and then in the next state, you decode it. But if you're in the access memory state for a load instruction, then you interpret the value in the memory as a data value, and then do something else with it, right? Okay. So the second, which has been very powerful, is the sequential instruction processing. One instruction is processed at a given time, fetched, executed, and completed. And the programmer assumes that you don't move to the next instruction before you finish the previous instruction, right? That's the sequential processing. And the program counter identifies the current instruction that's being processed. I don't like the term program counter, actually, even though we've used it many times. I'm going to slightly change it. You're not really counting a program, right? Now, if your mindset is sequential, you're really counting the number of instructions that you go through. But even that's not true because you may go back. Well, if it's purely sequential, you're really counting, right? I like the better name over here, which Intel uses actually in their ISA. It's the instruction pointer. Basically, that this is the address of the instruction that you're currently processing, and instruction pointer points to that address. We'll talk about pointers in the future, but that's what a pointer is essentially. It's also called a program counter. But basically, this pointer is advanced sequentially except for control transfer instructions. And that's the hallmark of the von Neumann architecture. Okay? Okay, so if you want to know more, you should read this seminal paper by von Neumann, Bergsongoldstein from 1946. It's a long paper. It's like 52 pages, I think, if I remember correctly. And it types it in a terrible font. But that's okay. You don't need to read it. I think I will require this one instead, the von Neumann model from chapter 4, Patel Patel, which beautifully describes the von Neumann model. Okay, keep in mind, stored program, sequential instruction processing. Now this gets back to your point over here, basically. There's a little bit more to the von Neumann model, but basically you have a processing unit, you have memory, and memory is unified, as you can see, and you bring stuff into the processing unit to be processed, and you have the control unit, which is sequential, and there's also input and output. Once you read the chapter, you will see. This is basically what most modern general-purpose processors look today. But again, this is not the only way to design a computer, as we've been experiencing recently and in the past also. So, I guess I'll ask the question for which you have the answer now. Is this the only way to design a computer? Is this the only way that a computer can operate, if you will? And your answer is no. Okay, good. I would have preferred a stronger no. Are people sleeping or something? Or you're Googling the Google's TPU unit? So yeah, the answer is no. A qualified answer probably is no, but it has been the dominant way. Meaning the dominant paradigm for computing for n decades, where n is, I guess, greater than 60 now. Okay, so let's stretch our minds a little bit. I want to give you a little bit different thing before we move into the implementation, because this is also this is a model of execution. Model of execution can happen at the ISA level as well as the microarchitecture level. So, for example, you could be sequential at the ISA level, but not very sequential at the microarchitecture level, right? As long as you hide it. We'll talk about that. Okay. Basically, let's take a look at von Neumann model. If you look at the von Neumann model, an instruction is fetched and executed in control flow order, right? As specified by this instruction pointer, program counter, if you don't like the instruction pointer so far. You're sequential unless you have an explicit control flow instruction. Basically, you keep incrementing that program counter going through the sequential program, and the programmer assumes that everything will be executed sequential unless you have a jump that goes somewhere else. But there is another model, and this is one of the other models, which is completely different. You don't have an instruction pointer. You don't say, oh, I'm going to fetch this next, and then increment the instruction pointer. Instead, I'm going to fetch and execute an instruction in the data flow order. If the data is ready for an instruction to execute, that instruction will execute. It will produce some result. Hopefully, it will make the data for another instruction ready, and that instruction will now execute. There is no order in this, except for the order of the flow of data, right? Whenever data becomes available, the instruction executes. This is called the data flow model. When its operands are ready, an instruction executes. Well, we've just eliminated perhaps the most fundamental thing that you've been working on since day one almost, right, in this course, the program counter, the sequential. So here the instruction ordering is specified by the data flow dependence, not something outside, not the memory address of an instruction that's incremented. And then each instruction specifies who should receive the result, if you will, which other instruction is the destination. So you really connect instructions with these pointers that say, oh, once this instruction finishes its result, send its result to this other instruction. Make sense? And an instruction can fire whenever all of its operands are received. So if an instruction is receiving operands from two different instructions, it needs to wait for both to be present, to be produced, if you will. And once both operands are produced, this instruction that's waiting for those can fire, execute. And potentially many instructions can execute at the same time, because you're not saying, I'm executing this instruction, like the instruction pointer. You're not doing that, right? You're saying, whenever the data is available, the instructions should execute. Well, maybe once the data value gets generated, it enables 1,000 instructions to execute, because all of them are waiting for that single data element, right? Maybe one instruction wants to add 1,000 to it, another instruction wants to add 1,000,000 to it. You can imagine many reasons, right? So this is inherently more parallel, right? Clearly, it's not limited by the sequential model that we have over here. So let me give you an example. Let's make this a little bit more concrete. I'll give you a toy example. Consider a von Neumann program that's written this way. I don't know, don't worry about what this does. Maybe cooked up. That's okay, but it's sequential basically, right? You execute this statement, only after that you execute this statement, only after that you execute this statement, ... Now let's be a little bit philosophical here. What is the significance of the program order over here? If this is the only thing that you want to do, why do you really care about program order? We'll get back to it in the future. But really, unless there's something weird going on, some external event that's interrupting your program, and you want to examine that program in the middle of execution, you don't really need that program order. Program order is there such that because you've written it this way, right? But let's look at something else. What is the significance of the storage locations? If this is the only instructions you have in the program, for example, V and W, what do you do with them? You're not doing much after that, right? They're really used to communicate this result to this instruction and this result to this instruction. Actually, this result goes to both of these instructions. And X and Y are also used to communicate the result of these instructions to here. And then let's say you print Z, do something. So that's the sequential way. But this is the data flow. Look at the same program, right? It's more graphical, if you will, because data flow tends to be more graphical. It's easier to show where the data goes based on a graph representation. In fact, this is called a Dataflow Node, and these are data flow arcs. Basically, if you look at this, you're inherently more parallel, right? You know that these two instructions can execute concurrently. These two instructions can execute concurrently. You know that these two instructions are ready when both of these instructions finish their results. And you know that this can fire or ready when both of these instructions finish their results. Does that look interesting? Yeah. Have you programmed this way? Has anyone here? Not, well, there's one person. That's good. Where did you program? Not to put you on the spot, but that's okay. If you program with something like LabVIEW, there's data flow programming models at the very high level. So you may have programmed it this way. But I guess I'll ask one other question for you. Which model is more natural to you as a programmer? Who says sequential? Okay. It's hard to see all hands. Who says data flow? Oh, no one thinks data flow. Maybe some people are like this. Is it because you're not used to it? You've always thought this way? Or is there something more fundamental to it? Anyway, I'll let you think about this a little bit. But these people have tried to build these computers a lot. And actually, all of the processors that you're using on your laptops are executing instructions in this way, underneath. But they're not showing it to the programmer. The programmer is writing programs this way, but processors are executing programs this way. Now, if you expose this to the programmer, that's a different issue. And we're not going to cover that in this course. We're going to cover it in a more advanced architecture course. But, for example, if you're writing a program on an FPGA, you don't really need to write it this way. You can directly write your program and embed it on an FPGA. Now, in your case, you're really building a processor on an FPGA. You're not writing a program. But if your task was to do this, you don't really need to do this in an FPGA. There are enough parallel resources in the FPGA that you do it this way, and then your result is much faster. So these things exist, basically. Data flow models exist. But let's talk a little bit more about that. I'll give you, I want you to stretch your minds and not be stagnant in some of the existing models. Okay, let me give you more on the data flow. Basically, in a data flow machine, a program consists of data flow nodes, as I said earlier. This is one example of a node. These are all nodes. A data flow node fires. It's fetched and executed when all its inputs are ready, meaning when all its inputs have tokens. Don't worry about the terminology maybe right now. Yes?
How does a node know when the inputs are ready?
Yeah, that's a good... You should take the advanced architecture course. Basically, well, we will talk about that in the out-of-order execution lecture, actually. You will see that whenever a data flow node fires, it sends its result to the destination. And the destination, there's a matching logic. that basically checks whether both inputs are ready. So you can think of this as an associative memory. You do comparisons. A node, whenever it fires, it sends its result to the destination, either directly. In this case, you basically send it to some memory location and set that bit for the correct argument in the memory location. And when both bits are set, there's some logic that checks, that's the matching logic, whether both bits are set. If both bits are set for your own operands, you can fire. Does that make sense? If you didn't understand it, that's okay. We'll talk about one implementation of it in out-of-order engines. But based on what I've described at the ISA level, this is a Dataflow node and its ISA representation. Basically, you have this operation, and you have the source node, 2 source nodes in this case, and you have the destination node that you need to send your result to. And if you need to send your result to multiple destinations, well, you could have either multiple destinations over here, or you could add another node that replicates, right? So it's beautiful, actually, right? So hopefully that was clear, actually. I think basically you know your destination in this case. In this case, it's simpler because you know your destination. You just send it to that location in memory and set the bit. And of course, you need also the argument, whether you're sending. So if you have a Dataflow node over here as the destination, you're sending it to the left one. So I'm sending to this instruction that's at memory location X, and I'm sending the left operand. And when that happens, there's some logic that sets this bit to 1. And then there's some other logic that determines the readiness of the instructions. So it's a little bit complicated. Now you can see how things go. So, but you can actually be creative. There are many, many Dataflow nodes. This is a conditional over here. Basically, input tokens are this. This is input data token and input control token. This basically implements a conditional branch, if you will, but it's really flowing the data, right? If the input control token is false, it passes the data token to the false output, like this. If the input data token were true, it would have passed the input data token to the true output. That's how you can direct the flow of the data. Relational is another one. Basically, it generates these true or false inputs. It checks if 10 is greater than 7 over here. It fires, first of all, when both of these results, both of these tokens are ready. And when it fires, it basically generates a true, because in this case, 10 is greater than 7. Right? It could have generated a false if the inputs were 7 and 10 on the left and right. This is a more complicated node. This is just to show this is a barrier synchronization. Basically, this is to synchronize all of the tokens. You want all of the tokens to arrive before you send them out some way. There could be one token that comes up over here, or there could be multiple tokens. This is, for example, this may be used to ensure that different threads of execution wait for each other, synchronize, and then move on to some other thing. My favorite example over here is a barrier-based program. You will get exposed to this in the future. But let's say you're counting the words in an entire book. And you want to have multiple threads that you want to operate on different parts of the book. You want to parallelize this task, right? If you do a single thread, a single thread goes through every single page and counts. Instead, you divide the book into, let's say, 16 threads. Each thread gets 10 pages, and each thread counts. How many... Maybe counting the words is not a good example. Let's say you want to get the histogram of different letters in the entire book. Each thread gets 10 pages and gets the histogram itself. Now, in the end, you want to add those histograms, right? But if you want to add those histograms, you first want to wait for every thread to finish its task so that you can do whatever comes next. Perhaps you add 2 threads in batches of 2 to get the entire histogram. Right? So basically, you need to insert a barrier synchronization such that you wait until all of the threads finish their task, and then you move on to a phase of the program where you do something else with those threads. Okay. But you can implement very complicated concepts, basically. But I'll give you a puzzle right now. You don't need barrier synchronization for this puzzle. But I'll give you one data flow program, and I'll ask you what it does. This could be a nice exam question, by the way. I wasted one of my exam questions here. But let me make things a little bit more clear for you. This is a 1 over here. This is n. Assume n is a non-negative integer. And then there's something that I didn't define. This is the branch node that you can see, right? This is a copy. That's what I discussed. If you want to copy an output, you create a copy. That's greater than 0, copy, branch, copy, decrement. This is decrement. This is multiply. And the result is this output. And this thing means that if the value goes over here, it dies, basically. It doesn't go anywhere else. That's the ground. And there's only one thing over here. This is the merging that's happening. Basically, you have n coming in, token. It gets consumed in the first place. But if there's another token that comes in over here later, you take that one. So you basically generate n only once. That's the input to the program. 1 and n are inputs to the program. Can you guys see this from the back? Okay, I'll give you a couple of minutes. Do you have the answer or not? Okay, there's one person. You're the first one to go, but I'll give others some time. You have the answer too? Okay, we have 2 takers. More solvers? Yes, one more. Do you have the correct answer, though? Hopefully. We'll check. I'll give you 2 more minutes. You have the answer too?
So is n positive, negative?
N is a non-negative integer. Positive integer. Okay, positive. I think non-negative works also, though. Okay. I think that's good enough. We have other material to cover. Who has the answer? Okay, that's good. I guess you get the first pick. M factorial, that's the right answer. I hope you didn't watch my online lectures. I'm just kidding. Yeah, this is M factorial. You have a separate answer? Does anybody have a different answer? Everybody has M factorial, at least those who raise their hands. So I will encourage you to do this yourself, but basically what's happening here is, let me go through it very quickly. This node fires immediately. No. Its data token is available. So there are 2 tokens available initially in the program, right? 1 and n. Clearly 1 will not fire because it's waiting for this Boolean which is not available. But n will fire because n will go and then you copy n. Basically, this will be n over here. This will be n. Clearly, it's not going to fire because this is not available yet. But this is going to fire. n greater than 0 produces a true, and true gets copied over here, and both of them fire at this point because they were waiting for their Boolean token. Well, I said true, but true assumes that n is greater than 0, right? Let's start with that example. Let's say n is greater than 0. True means that you get 1 out of this output. It doesn't go this way because that's the function of this Boolean. But this doesn't fire because this is waiting for this stuff. This was true means that you basically get a copy of n over here, which gets copied over here. Basically, you get 1 times n over here, and then you get n minus 1 over here. Now you do the same thing with n minus 1 over here, and then n over here, right? And then you will find out soon that you get n times n minus 1, and then n times n minus 1, n times n minus 2, dot, 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 until n becomes 0. Once n becomes 0, you get a false here, and then this basically kills the input token, sends it to the ground, and this basically sends you the output, and there are no tokens left in the program at that point. Make sense? It's simple. Now, this may not be the best way of implementing n factorial in a Dataflow program, but that's a different issue, right? It's really an iterative. Basically, we're basically at a loop in the Dataflow program to implement n factorial. Okay. Now you've stretched your minds. Let's look at some other things. Do we need an instruction pointer in the ISA? Again, this is, if you were an ISA designer, you have a choice, right? If your answer is yes, basically you've committed to control-driven sequential execution at the program level. And we've already discussed this. If your answer is no, you have data-driven parallel execution. An instruction is executed when all its operand values are available. Now the programmer needs to program in this way. Now there are many trade-offs over here which we're not going to get into. In the more advanced architecture course, we will cover some of these. But ease of programming for average programmers. Sequential execution is very easy, actually, it turns out, for many programmers. This may be a little bit harder. Ease of compilation, how do you compile to it? Performance, which one has better performance? Now this becomes interesting right now because even if you have a program like this, maybe you get a lot of performance out of it. Hardware complexity. I'm not going to cover all of this. This is just to have you think about all of these issues. Because if you make a decision like that at the ISA level, it affects everything, basically. So I've just given you an example, ISA level trade-off. But we're going to cover more microarchitecture level trade-off in this lecture, in this week, basically. A similar trade-off, control versus data-driven execution, can be made at the microarchitecture level as well. Right? Basically, ISA specifies how the programmer sees instructions to be executed. Microarchitecture is how the underlying implementation actually executes the instructions. You can say programmer sees a sequential control flow execution order, or programmer sees a data flow execution order. And independently, microarchitecture can execute instructions in any order, as long as it obeys what you promised the programmer. Right? As long as it gives you the correct result, and it obeys this contract, right? When making the results of an instruction visible to the software. Basically, programmer should see the order specified by the ISA. And the key idea of out-of-order execution is, in modern machines, you have the von Neumann model at the ISA level. Programmer sees sequential control flow execution, writes programs, assuming an instruction is executed only after the previous instruction is completed. Whereas the hardware reorders those instructions internally, but when it reports back to the software, it reports back the sequential model. Okay, so let's look at this process instruction step a little bit. Basically, ISA specifies abstractly what the architectural state prime should be given an instruction and given an architectural state. It's really an abstract finite state machine, right? At the high level, ISA is that way. You have the state, that's programmable visible state, and you have the next state logic, which is the instruction execution specification. For any finite state machine, you've learned about those. You need state and a next state logic. And the next state logic produces the next state, right? From the ISA point of view, there are no intermediate states, right, between the architectural state and architectural state prime during instruction execution. But that's completely different at the microarchitecture level. Well, from the ISA point of view, you have one state transition per instruction. At the microarchitecture level, we implement how architectural state is transformed to architectural state prime. There are many choices that you have in implementation, assuming you're bound by this von Neumann model. We're going to assume von Neumann model for now. We can have programmer invisible state to optimize the speed of instruction execution. For example, multiple state transitions per instruction, and that's what we're going to talk about. But what you've seen in the previous lecture last week is this. Transform architectural state to architectural state prime in a single clock cycle. That's choice 1. But we're going to see this choice 2. You take architectural state, when you're executing an instruction, transform it to some architectural state plus microarchitectural state 1. That's one step. And then you take the next step, transform it to some other microarchitectural state without modifying the architectural state. And then you transform it to another microarchitectural state. And in the end, you produce the result of the instruction, architectural state prime, that you report to the programmer. You basically take multiple clock cycles to transform an input architectural state to an output architectural state. Now let's look at what you've seen so far. Basically, this is one of the most basic, but as I will show you, a contrived way of designing processors. Each instruction takes a single clock cycle to execute. You basically use only combinational logic to implement instruction execution, because you have the state and then the next state logic. Next state logic is combinational. There is nothing sequential there. There are no intermediate programmer invisible state updates. You basically take this, process the instruction in one clock cycle, produce this, architectural state prime. And if you are more visual, it looks like this basically. This is the input, architectural state, next state logic, architectural state prime. And we've already seen in the last lecture that the clock cycle time is determined by the what? Yes. That's true, yes. But what determines the clock period? Yes. The longest path, sure. But what determines the longest path? Okay, yeah. I'll ask you the next question. I knew that you were going to answer this way. What is the critical path of the combinational logic determined by if you're designing the single cycle machine?
By the propagation delays of the components.
Say it again?
By the propagation delays, propagation delays of the components.
That's true, yes. But think about the instructions. Which instruction is determined by? If you remember the last lecture, yes?
Well, the one that takes the longest to execute.
Absolutely, yes. The one that takes the longest to execute, right? Not all instructions are equal. Some instructions are fast. Now we've clicked on the question and the answer. Some instructions are fast, some instructions are slow. And the one that takes longest to execute determines your clock cycle. Now, you've seen in the previous lecture that this was load word, right? You guys remember that? It was load word because load word required multiple memory accesses to fetch the instruction and then to fetch the data and then other stuff in between to generate the address. It's not always load word, but it's usually the loads because they require at least 2 memory accesses, right? Depending on what it needs. Depending on the ISA specification, of course. So let me go very quickly to the programmer visible state. I've been talking about this, but I just want to make sure that you guys we are on the same page. Basically, programmable visible state is really the architectural state, right? And it consists of memory, registers, and the program counter. These are the registers in the ISA, right? This is really your programmable visible state. There's also I/O state, but we're not going to deal with that for now. And instructions and programs specify how to transform the state to the next state. So, okay. We've discussed this. The big disadvantage of a single cycle machine is the slowest instruction determines cycle time. You have a long clock cycle time as a result. Because there are fast instructions also. Add is fast, right? If you're adding 2 registers, all you need to do is to fetch, decode, access the register file, do the add, write the result back to the register file. There are no long memory accesses. So it doesn't make sense to actually set your clock cycle time based on something much, much longer, even though you can finish the add in only, let's say, 200 nanoseconds or something. Multi-cycle machines, so let's say memory access is 200 milliseconds, add is 200 nanoseconds. Does it make sense to make your clock cycle time 200 milliseconds? I know I'm exaggerating, but that's exactly what we're doing with a single cycle machine. That's why it's contrived. On the other hand, in a multi-cycle machine, instruction processing is broken into multiple cycles or stages. And as I said, state updates can be made during an instruction execution. You don't need to wait until the end of the instruction's execution. And only architectural state updates are made at the end. Because if you update the architectural state in the middle of an instruction, that's bad. The programmer should not see it. Right? You really want to preserve the model to the programmer. The programmer is expecting an update to the memory location, for example, only after this instruction executes. Right? That's the von Neumann model. Now, you may ask, why is this a big deal? Well, think about somebody inspecting that memory location from the outside. Right? They shouldn't really see any intermediate states other than what's specified by the program. And when would someone inspect your memory or registers from the outside? Well, have you ever debugged programs? A lot, right? Or you're going to debug a lot, I promise you that. If you're debugging a program, and if you set a breakpoint, you're really saying, oh, I want this program to stop at this point. If there were some intermediate updates that happened that didn't allow that, then you have a problem. It's a nightmare to debug that program because your machine didn't really obey the semantics of the ISA, right? That should not happen. Your machine should always obey the semantics of the ISA. So the advantage over single cycle, we'll take a break in a couple of minutes. The slowest stage determines the cycle time. This is very different from the slowest instruction, right? Why? Slowest instruction, you're really bound by the specification of the ISA. I can give you an instruction that says, copy this string to this other string, and this string is 1 billion elements long, right? That's a very long clock cycle time with this really contrived machine model. But now with the stage, as a hardware designer, you have all the flexibility. You can say, my clock cycle time is going to be 100 nanoseconds, period. That's it. I don't care what instructions I'm going to execute. I'm going to break it into 100 nanosecond chunks. And every instruction is going to take enough 100 nanosecond chunks until that instruction is done. If memory requires 200 milliseconds, it's going to take 200 milliseconds divided by 100 nanoseconds stages. If an add requires only 200 nanoseconds, it's going to take 200 nanoseconds divided by 100 nanoseconds, 2 stages. Right? That's it. 2 clock cycles. Okay, we already discussed this. Let me finish these 2 slides and then we'll take a quick break. I want to tell you what the step-by-step is, basically. We've talked about clock cycle, but there's another cycle, instruction processing cycle. Basically, instructions are processed under the direction of a control unit step by step. An instruction processing cycle is basically the sequence of steps to process that instruction. This is kind of obvious, but we should talk about it. Fundamentally, there are 6 steps. You fetch an instruction, you decode the instruction, figure out what it is supposed to do. You evaluate the address of the instruction. For example, for a load, you evaluate the address. You fetch the operands. You basically, for example, you fetch from the register file or memory, depending on the instruction type. You execute the instruction. ALU operations have that execute stage. You store the result. Not all instructions, of course, go through all of these, right? A jump operation, for example, may not go through a lot of these. Address evaluation is not required for non-memory instructions. It may be required for jump instruction. Also, it depends on how you define some of these. But basically, you should, the reading that you have will discuss that. So in a single cycle machine, all 6 phases require a single machine clock cycle to complete. But in a multi-cycle machine, you can have multiple clock cycles. And each phase, in fact, can take multiple clock cycles to complete. Well, let me finish this one also. Sorry. But basically, you transform data to data prime when you operate architectural state to architectural state prime. And this transformation is done by the functional units. These units need to be told what to do with the data, right? So we have two components, and you've already seen these, but I want to name them. We have the data path component. Data path component basically consists of hardware elements that deal with and transform the data signals. Right? These are the functional units, hardware structures that enable the flow of data into the functional units, like wires and muxes, and the storage units that store data, like the registers and memory. This is all data path, and you know this, that's why I'm going through this fast. On the other hand, control logic controls, basically it consists of hardware elements that determine the control signals. Basically, it's signals that specify what the data path elements should do to the data, right? Which mux input should be taken, right? Which one do you select? Or what should the ALU to the data, do to the data? Or which register should you read from, right? Which register IDs should you use when you're reading from the register file? So this is very fundamental. The data path and the control logic separation is important. And you've seen this when we designed the single cycle machine last week. But you're going to see this going forward also. Okay, let me stop over here because I want you guys to start afresh. Let's take a break and then we'll continue. All right. Is this lighting better for some of you, or is this too bright over here? How do I do that? Let's see. Turn off this one. How do I do that? I always have this problem. Is it projection? Let's see. No? It's too dark over there? Okay, let's see. How about this? I'm not sure if... Okay, this is good. What do you think? Okay, good. All right, let's continue. I'm going to go through some of these relatively quickly. Okay, there's another difference between single cycle and multi-cycle, and that's about when you generate the control signals that operate the data path. Basically, if you look at single cycle, a lot of things are serial. Control signals are generated in the same clock cycle as the one during which data signals are operated on. And this could be problematic if control signal generation takes time. Now, you could be limited by how long it takes to generate your control signals. We will see that more clearly soon. Whereas in a multi-cycle machine, control signals needed in the next cycle can be generated in the current cycle. Basically, you overlap the processing in the data path in the current cycle with the control signal generation for the next cycle. Meaning that you've just eliminated control signal generation from your critical path of execution. You can now parallelize, right? It's very difficult to do in a single cycle machine. Basically, you get more parallelism. This will become more clear when we talk about micro-coded machines. In a micro-coded machine, you basically generate the control signals for the next cycle in this cycle, and then you use them in the beginning of the next cycle. Okay. So data path and control, there are many ways of designing these, and that's exactly what we're covering, single cycle, multi-cycle pipeline. You can have single bus versus multi-bus data paths. You can have hardwired combinational control, which you've seen, or micro-coded microprogram control, which you have not seen so far. So basically, the difference between these two is control signals are generated by combinational logic over here, or control signals are stored in a memory structure, and you basically sequence through that memory structure with your finite state machine. Okay. And control signals as structure clearly depend on the data path design, because you're really controlling your data path, right? Okay. I'll also remind you of the performance analysis a little bit. We've covered this briefly, but I want to go a little bit longer on this. Basically, the execution time of an instruction is determined by two things, right? Cycles it takes to execute that instruction, cycles per instruction, and the clock cycle time that you have in your machine. Execution time of a program is basically the summation of this across all of the instructions that you execute to complete the program. Right? This is, again, single-threaded von Neumann machine. Another way of expressing this is you basically have number of instructions times the average cycles per instruction times clock cycle time. You've seen this before, but it's important that this average CPI is one thing you can optimize for. Clock cycle time is another thing you can optimize for. Number of instructions is another thing you can optimize for. We're not going to change that right now. But in a single cycle machine, you have your hands tied, because your cycles per instruction is always 1, and your clock cycle time is long. Right? The big benefit of multi-cycle is your cycles per instruction is different for each instruction, and the average CPI is hopefully small, but you don't know that. And clock cycle time is hopefully short. In fact, you could make this as short as you want it to be. We will talk about this determining clock cycle time when we talk about pipelining, but a lot of this applies to multi-cycle machines also, because you don't want to make your clock cycle time too short, because there are overheads associated with register setup and hold, right? There's also jitter overheads. There's useful part of your clock cycle, and there's not so useful part of your clock cycle. If your overheads become dominating, you're really wasting a lot of time to latch the data into the registers, right? So too short is not always good. Too long clearly is not good. So you really need a balance. In fact, there have been a lot of papers written to discuss what is the optimal clock cycle time of a processor. And people don't agree necessarily. But we'll talk about that. So, but the key point here is multi-cycle machine, you have 2 degrees of freedom to optimize independently. The cycles per instruction and clock cycle time. You don't have that freedom in the single-cycle microarchitecture. So this was the single-cycle processor that you guys designed last week, in the lectures, at least. It's very simple. It doesn't cover a lot of things, but it's nice, right? It clearly has some disadvantages, like why do you have two memories over here? How do you get 2 memories to begin with? 2 ports. But we haven't talked about ports yet. And then a bunch of adders, right? You have 1, 2, 3 adders. Actually, it's an ALU, but consider that an adder. But it's a bit wasteful, right? So we could do better than this. This is another example of a single-cycle processor. I just want to give you an example because there's only very few ways you can design a single-cycle processor, actually. This is from another book. This is from Harris and Harris, which is your textbook, which was discussed. And this is from Patterson and Hennessy, their computer organization book, which has a few more instructions over here. But if you look at it, the design is very, very similar, right? In fact, you see 3 adders over here also, and 2 memories over here. Now, these guys probably looked at each other also when they were designing the machines, but that's beside the point. Single-cycle machines, you don't have a lot of freedom to design. Let's evaluate this. You did evaluate it in the last lecture, but I want to go through this. I'll first pose you this question. Is this a good idea design? I think that's clear that it's not. But it could be a good idea or a bad idea depending on your constraints, always. If you never access memory, maybe that's a good idea. But that may not be very realistic. Okay, let's do the analysis. Basically, CPI is strictly 1. How long each instruction takes is determined by how long the slowest instruction takes to execute, even though many instructions don't take that long to execute, right? We've already said this, so I'll just jump through this. Basically, different instructions go through these different stages, and I've collapsed them into 5 over here. One question is, do each of the above phases take the same amount of time for all instructions? Well, that's not necessarily true, actually. But let's assume some time for different instructions. This is based on the slide in Design 29, basically Patterson and Hennessy book. Again, you don't need to know exactly how this design is, but it's very similar to what you've seen last week. Okay, I'm going through this quickly, but you know all of this hopefully. So this is basically the analysis that we do. Memory units take 200 picoseconds, read or write. ALU and adders take 100 picoseconds. Register file takes 50 picoseconds, and we're going to assume generously that other combinational logic is 0 picoseconds. It's clearly not true, right? But that's okay. We're approximating here now. So even with these assumptions, you see that there is a huge variation in the delay to execute different instructions. A load takes 600 picoseconds over here, right? Whereas a jump takes 200 picoseconds, right? So there is a big difference in this case. But in a single cycle machine, you got to make everything the worst case. Everything executes 600 picoseconds. And you would be lucky, I think, if you get your memory to be 200 picoseconds, right? There are a lot of assumptions over here. So we could play the game of let's find the critical path on this design. You did play that game in the other design. But load word execution is the critical path in this case. Let's take a look. Basically, how do you find the critical path? You go through every single instruction and exercise the paths. This is R-type and I-type ALU instructions. Basically, the critical path for this instruction goes through the ALU, bypasses the memory because it's not a memory instruction, and then writes into the register file, right? It goes through this part. There's also an update of the program counter with every instruction, but that's, at least in this case, not on the critical path. In a single cycle machine, that's not on the critical path. That's going to change in a pipeline to out-of-order execution machine. This determining the next program counter can be on your critical path. Now you're saying, PC plus 4, how complicated could it be, right? Well, if it's a jump instruction, what do you do if it's a branch? Okay, anyway, let me not digress. This is 400 picoseconds. That's how you get that. Load word, it goes through memory twice, right? Memory, it reads the registers. It goes through the ALU. That's the 100 picosecond addition over here. It goes through memory, and then it writes back into the register file. That's why it basically has a large latency. It's 600 picoseconds under the assumptions that I've shown you over here, but remember the last lecture? It was 925 picoseconds. It doesn't matter. It's all based on assumptions, right? Or based on the real measurement that you have in the critical path. Store word, 550 picoseconds. It's not 600 because it doesn't write to the register file, right? So it's a little bit shorter. Branch taken, usually shorter, but you can see that the critical path of a taken branch goes through this part. Basically the update of the program counter, right? With our assumptions, it's 350 picoseconds over here. And it's really update of that program counter determined by the branch condition, right? This path also is a potential critical path, but it's not your critical path because this signal to this mux, which basically determines what is your branch condition, if it's taken or not taken, is the later one to arrive over here. Okay? Jump is not that interesting because you determine your address very quickly in a jump. You don't go through the ALU to determine the branch condition. It's an unconditional jump. So basically, as you've seen, the critical path goes through the load, in this case also, as you've seen in the previous last week as well. Okay, we went through this exercise just to warm you up, basically. All of you are familiar with critical path analysis now? Excellent, yes. You will do that a lot. Now, if you actually had a competition of your designs, maybe you would do it even more. But that's okay. So what about the control logic? How does that affect the critical path? This is a good question to think about, I think. Can control logic be on the critical path? Absolutely, yes. If you design your control logic to be long, such that the signal arrives the latest, your control logic is on the critical path, right? For example, there were machines, Control Data Corporation's 5600 machine at a control store base. It was a microprogram machine. And the control store access was too long. As a result, it was the critical path. So they actually did a lot of hoops to make their control logic pipelined. But we're not going to talk about that. So whenever you're designing a machine, you should be very careful about the critical path. Control logic can affect it, data path can affect it, and you really need to be cognizant. Okay, slowest instruction process. I've given you already load word, but I will exacerbate this because memory is really not magic. So far, we're assuming memory is magic, right? You have this memory over here in, I don't know, whatever time, we're going to get the results. Well, good luck with that with the memories that we have today, right? Which memory that you know of today is accessed, I don't know what we assume, 200 picoseconds, right? That's not going to happen. Even if you have a cache, which we will talk about in more detail, let's assume that everything hits in the cache. Well, that's again a very bold assumption, right? This only works if everything hits in the cache, but it doesn't. So what if memory sometimes takes 100 milliseconds to access? Maybe milliseconds is too much, but I want to exaggerate. Is your clock cycle time 100 milliseconds? That sounds stupid, right? You don't want that. That's exactly why the single cycle architecture doesn't make sense. Basically, does it make sense, if this is the case, does it make sense to have a simple register-to-register add or jump to take 100 milliseconds plus all else to do a memory operation? It clearly doesn't. And what if you need to access memory more than once to process an instruction? Which instructions need this? Memory instructions, right? But every instruction really accesses memory once in the fetch stage. Right? All instructions require memory access because you need to fetch the instruction from memory. And if you have a good instruction cache, you hit in the instruction cache, and that's hopefully quick. But if you miss in the instruction cache, now you're waiting for a long time. Okay, we'll get back to that later. So basically, to bury a dead architecture, finally, single-cycle microarchitecture is not only complex, but it's also contrived because of this reason. All instructions run as slow as the slowest instruction. It's inefficient because of that reason. And you must provide the worst-case combinational resources that's required by any instruction in parallel. Right? That's why we need 3 adders. That's why we need 2 memories, because that's the worst-case requirement, because you do everything in a single clock cycle. Basically, you need to replicate a resource if it's needed more than once by an instruction during different parts of the instruction processing cycle. Remember the instruction processing cycle, 6 steps. It's also not necessarily the simplest way to implement an ISA. I gave you the example of repeat move S. I didn't call it repeat move S, but basically in x86 architecture, there are very, very complex instructions. And one instruction is there's a counter register called ECX, count register, while the value in count register is not 0, you start with a positive value, is not less than or equal to 0, let's say, that way. Copy byte from the source. I should write it down. Come on. That's better, right? And we're going to test this one also. Basically, you do a byte-by-byte copy or word-by-word copy. It's actually much more complicated instruction than that. But apparently, yeah, there you go. PC. This is called... Do you see it? I need to switch it on. It's trying to power up. Do you think it'll succeed today? Maybe. Okay. What do you think? That's HDMI out. This used to work. You guys know what I'm doing wrong, if anything? Oh, okay. Just required some time. Okay. Now it's not projecting. It's accessing memory. That's what it is. Okay. Let's see if I can do this. So basically, you set a while. Can you see it? ECX greater than or equal to 0. Memory EDI equals memory ESI. I guess I could have made it a single line, but that's okay. And then EDI plus plus, ESI plus plus, and then ECX minus minus. I could have been fancier by adding the minus minus plus 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 over here, right? It would still be a correct C program. And of course, you initialize ECX. That's the input to the instruction over here. But this is a single instruction in x86. It's a complex instruction machine. That's why it's called a CISC machine, complex instruction set computer. And there is no limit on what ECX could be. In fact, I've analyzed when I was at Intel programs where people do write these things. People copy 1 million elements. How do you design this in a single cycle, right? You could do 1 billion elements, right? It makes no sense, right? So the way this is implemented in the Intel architecture is, well, in microarchitecture, is through microcode. Basically, what we will discuss a lot tomorrow. You basically go through a microsequencer that sequences through this little program, if you will. But this little program is a single instruction, really. It's not a program. It gets translated into micro operations that you sequence through internally. And we will see that. That's one way of designing a multi-cycle machine, actually. You treat an instruction as a sequence of micro instructions and design a control logic such that it sequences through those micro instructions. Now you can do many, many things. You can have your little program inside an instruction, right? You could branch. In fact, in Intel calls this micro branches, if you will, because they're not real branches, but they're micro branches. So this would be a micro branch, for example. And this would be a micro add. This would be a micro add, micro subtract, and in fact, this by itself shows you the complicated ISA, right? Basically, you copy a memory location to another memory location. But this instruction, I wrote it nicely over here, by the way. If you look at the Intel manual, it's like more than a page, because there are other things that you need to check during this instruction. But this is a beautiful instruction. Good thing that we are not implementing it in this. Okay, let's go back to, if we can. Okay, good. So there are other instructions like this. VAX, virtual address extensions. This is before Alpha, Digital Equipment Corporation, had this ISA. It had an index instruction. That's another complicated instruction. The complexity was basically you would do an array access, a multi-dimensional array access. I believe it's a 3-dimensional array access with bounds checking. Every single access had bounds checking on the arrays. And that was a single instruction. You don't want that to determine your clock cycle time either, compared to an add, right? So you get my point. Basically, also, it's not easy to optimize and improve performance, right? Optimizing the common case doesn't work with a single cycle architecture because you may have some common instructions. Your most common instruction could be an add. And you're not optimizing for that. The latency of the add is determined by the latency of this humongous repeat move S. That's why single cycle doesn't work, basically. You always need to optimize the worst case all the time. And optimizing the worst case is really hard because you have very little margin to optimize that worst case over here. Okay, this brings me to the design principles, which are really important. So I'll spend some time on these. There are 3 architecture or microarchitecture, this is more microarchitectural view, design principles that you should come away with in this lecture. One is critical path, the other is bread and butter or common case design, and the third is balanced design. Critical path, basically, is very suggestive, right? You want to find and decrease the maximum combinational logic delay when you're designing a microarchitecture. You break a path into multiple cycles if it takes too long. Of course, the assumption here is you're designing a high-performance microarchitecture, right? You should always clarify the design point. Like, what is your goal? High-performance microarchitecture. So clearly, this is a good design principle. Single-cycle microarchitecture doesn't allow you a lot of freedom on that one. Basically, you want to reduce the critical path of your longest instruction, but you don't have a lot of freedom, right? Bread and butter, common case design says, spend time and resource on where it matters the most. What are you executing? Improve what the machine is really designed to do. Of course, it's an art, right, as we've discussed earlier. You may know a common case, and you really want to optimize that common case first. There's also Amdahl's law. You guys know about Amdahl's law? Yes, excellent. So Amdahl's law suggests that you should optimize for the common case because that's where you get the most benefit. Again, a single cycle architecture, as I just said, it's very difficult to do that. Well, you're not doing that clearly because unless your common case is the worst case, You're not optimizing for the common case. And this will come up in many cases, in many designs that we will see. And the third is the balanced design. Critical path is an example, a specific example of balanced design, I would say, but it's not exactly balanced design. Balanced design means you want balance across the different hardware components. One balance is you want your cycle time to be balanced. You want the work that is done in different phases to be balanced. You don't want the amount of work in a given cycle to be, let's say, 200 picoseconds, and in some other phase you only use 10 picoseconds of that cycle. That's not a very balanced division of phases into the cycles, right? But there are other examples of this. You want to design to eliminate bottlenecks. For example, we will talk about superscalar processors. If you can execute 20 instructions, let's say if you can decode 20 instructions per cycle, does it make sense to fetch only 2 instructions per cycle? Probably not. That doesn't sound like a very balanced design, right? So you really want to balance the flow of instructions inside your pipeline. Now we will see examples of this. So single cycle design doesn't favor very well. Doesn't fare very well in light of these principles. And I'll let you think about that because we've already bashed single cycle designs quite a bit. I'll give you some aside also. System design principles. I think it's always good to think about principles, right? We're going back to the first lecture. When designing computer systems and architecture, it's important to follow good design principles, right? Principle design, remember, I showed you Frank Lloyd Wright's design. Architecture should be based on principle, not upon precedent. And I gave you some examples. This is the precedent, and this is more principled design. And you remember the principle. If not, you should go back to the lectures. So people develop system design principles. There are many of them. We'll continue to cover them. But I will give you some reference if you're interested in these. Some of them are older, some of them are newer. And this is actually a nice one also, hints for computer system design. You can refer to these slides. These are not required readings. In fact, I'd rather do your labs. I'd rather that you do your labs rather than these readings. But if you have time before going to bed or something, you can read that. Or good reading with beer. Okay. So I will give you one key system design principle, though, that's really, really important. And this comes up over and over and over and over. And this design principle always wins, in my opinion. And that's keeping it simple. Simplicity is really the key design principle. And we will see that in micro-coded machines. Do you guys know who said this? Yes, that's right. Basically, everything should be made as simple as possible, but no simpler. And this is true, of course. If it's too simple, it may not work. And of course, keep it low cost. This is applied to what we've done. I don't know who said this. If you guys know, let me know. An engineer is a person who can do for a dime what any fool can do for $1. So cost is, again, something that wins. And for more, see Butler-Lampson's hints for computer system design. Now, we've already covered some multi-cycle, but let's go into it a little bit more detail. Basically, the goal, there are some other goals, peripheral goals also, like reducing the hardware cost, making things simpler, lower cost. But the goal I will motivate this with is letting each instruction to take close to, or let's remove that close to, only as much time as it really needs. That's the ideal that you would like, right? If an instruction finishes quickly, you should spend only that much amount of time. If an instruction requires a long time, you should spend that much amount of time. Now, this is a challenge to achieve, even with multi-cycle designs. Because the way we're going to design them is we're going to set a clock cycle, right? Whenever you set a clock cycle, you introduce overheads. If your clock cycle is too long, something may finish earlier. If your clock cycle is too short, you have other overheads, right? So the idea is determine the clock cycle time independently of instruction processing time. Each instruction takes as many clock cycles as it needs to take. And we've already covered this. Multiple state transitions per instruction. And the states followed by each instruction is different. And we already seen this. This is just to jog your memory. That's why it says remember. Okay, basically we're going to do this. It's pretty simple, right? Sounds like a pretty simple idea. But a lot of the things that we will see later on will build upon this. Process part of the instruction in one clock cycle, process the next part, until you're done with the instruction. And now you can produce the architectural state, prime. And your input is architectural state. And all the while over here, you don't modify architectural state. You produce intermediate states. Now, immediately, intermediate states need to be stored somewhere. And that's exactly your overhead, right? Everything comes at a cost. There's no free lunch. And your cost over here is, you process part of it, you stop. Well, you got to save your data somewhere, right? That's the intermediate result. You need registers for it, which did not exist in the single-cycle microarchitecture, right? You saved your state only at the end to the architectural state. There is no registers added. That's the cost we're paying here. Okay, let's look at the benefits in terms of the design principles. Critical path design, it looks good. You can keep reducing the critical path independently of the worst case processing time of any instruction, right? As I said, you can say, I want my processor to run at 30 gigahertz. And I'm going to set my clock cycle time to that. And now I'm going to design my finite state machine around that. Common case design, you can optimize the number of states it takes to execute important instructions, right? That make up much of the execution time. You didn't have this freedom in single cycle. Balanced design, there's no need to provide more capability or resources than you really need in this case. We're going to get rid of some of those adders. Basically, an instruction that needs a resource X multiple times doesn't require multiple of those X's to be implemented, right? Because you use that X in this step, and then you reuse that X in the next step, as long as you design data path and the wires such that you can reuse a data path element many times. And this leads to more efficient hardware because of what I just said, actually, that the slide repeats. And downsides, make no mistake, there's always an upside and a downside to every single idea that you're going to encounter. If you don't come up with a downside, it's probably because you're not thinking critically enough. And if you don't come up with an upside, either the idea is really horrible, or you're probably not thinking critically enough. I would argue the latter. But I want to reserve the case that the idea might be really horrible also. Okay. So that's basically what we said, right? You need to store the intermediate results at the end of each clock cycle. And this could lead to a lot of overhead depending on how much intermediate results you generate. Basic hardware overhead for registers. And also there's another overhead, latency overhead, right? Register setup hold overhead paid multiple times for an instruction. Because you're going through. This is basically the clocking overhead, if you will. Okay, performance analysis, we've already covered this actually. Basically, it's not easy to optimize this design, but it's going to be easy to optimize this design. So let's take a closer look in the remaining 10 minutes. We're going to cover this tomorrow, but I want to introduce you Maurice Wilks. He's basically the father of microcoding and microarchitecture in general, actually, I would say. Microarchitecture existed before him, but he really put into it more formalism and a lot of creativity. So one elegant implementation of a multi-cycle architecture is the concept of microcoded, microprogram machines. But I'm not going to cover this because we don't have enough time. We're going to postpone it to tomorrow. But I'm going to give you another design, not necessarily microcoded, which may or may not have issues, depending on how you do it. But before we go into it, let's look at the key idea for realization. Right? Basically, you can implement the process instruction step. That's exactly what we're doing with an instruction. We're implementing this process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. Right? Remember the 6 steps? I'll give you a pictorial view of it also. A state is defined by the control signals asserted in it. It's really the definition of a state, what control signals you have. And control signals for the next state are determined in the current state, or could be determined. You don't have to do it this way if your control signals are not determining your critical path. So this is basically what we're going to do. We're going to break this into a sequence of states for every single instruction. Some of these states will be shared. Fetch and decode is shared across all of the instructions. But then you can jump to little subsequences of the finite state machine or subgraphs in the finite state machine for different instructions, right? And eventually, every instruction returns back to the fetch state. Basically, we divide the instruction processing cycle into states. a stage in the instruction processing cycle can take multiple states, and you sequence from state to state to process an instruction. And the behavior of the machine in a state is completely determined by the control signals, as I said. And the behavior of the entire processor is specified fully by this finite state machine. Basically, all you have is really a finite state machine in this case. Of course, in a state, control signals control two things: how the data path should process the data, and how to generate the control signals for the next clock cycle, or maybe the current clock cycle. I'm a big proponent of generating control signals as early as possible, of course, without wasting resources, because that's one principle that minimizes the potential of your critical path extending. If you generate your control signals earlier in a previous clock cycle, by definition, you're hopefully eliminating the possibility of extending your clock cycle, current clock cycle, due to the generation of those signals. Okay, one example, microarchitecture. Remember, this is the single-cycle MIPS processor. We're going to really quickly turn it into a multi-cycle processor. Well, you can go over this. This is basically what I said in the context of this. But basically what we want to do is, let's be a little bit more practical as well in the design choices. So let me define what we're going to do. We want to basically get rid of the two memories. We want to have only one. We want to get rid of 3 adders. We want to use the ALU for all operations. That sounds good, right? More efficient design, more energy efficient also, hopefully. And we've already discussed this. So let's start with the longest instruction, load word. And you know that we have the base plus offset addressing, and this is the destination register. We need to basically do all of this. This is basically the steps that load word needs: fetch instruction, read operands, evaluate address, access memory, store result. Right. So you need to first design the data path, just like we did for the single cycle data path. You need to design a data path for this. Well, you consider each step, right? One is fetch. We're going to arbitrarily divide this into steps right now. As a result, we're going to get bad performance, but that's okay to begin with. So this is the first fetch instruction, right? You fetch the instruction, you input the PC over here, and you enable. This is the register that we added, basically. You produce an intermediate result. That's the fetched instruction. That's an instruction register. That's the cost we pay, right? We just added a register over here. Now your clock cycle is this short, right? But we haven't added other stages yet. The next step in the processing of the load is access register file. Let's assume that we put another clock cycle at the end of that, basically another register. This is the second step. And of course, control signals need to be set correctly, but in this case, there are no control signals because register file is always read once you put an input over here. And the next step, and for load immediate, you need assign extended immediate, if you remember the load instruction. This is the next stage, basically. This is the load address. Basically, you need to generate the address over here. To generate the address, you need to get the data from the previous stage, previous intermediate result, and instructions last 16 bits, sign extended as the other input of the ALU. You need to do an addition in the ALU, which means that you need to set the control signal accordingly, and you get the ALU results, and we arbitrarily say, okay, that's the end of this step. So we add another register over here. Now you can keep adding registers. As you can see, we're adding overhead, right? And the next stage is you read the memory. You basically need to provide the data path to be able to read, to supply the address that you just generated to the same memory. We're going to reuse the same memory. And then get the data out, and then latch the data. Memory access takes long, so we're going to latch it right away after that. Another register. And then the last phase in this instruction processing for load is basically you get the data, and you write it to the destination register specified by bits 16 through 20 of what we've stored in this instruction register. So we make use of those intermediate things that we've stored in previous parts of the instruction processing cycle, right? Does that make sense? Is that clear? Okay. So it's beautiful. This is kind of minimalist right now. I don't know if you can do better than this. Of course, you can have less fewer stages, but that increases your clock cycle time perhaps. And you could argue that this may not be the best way of dividing these into clock cycles, right? For example, some of the register file access takes short. Maybe we combine it with something else over here. I don't know what that something else is now. So, of course, we forgot one thing, perhaps the most important thing from the von Neumann standpoint, which is incrementing the PC. Right? So you need to provide the data path to increment the PC also. And this is similar to what we've seen before, except it goes through a different looking data path over here. Basically, you need to supply the PC, current value of the PC, and then you need to set the control signal such that you get source A here and add 4 to it, in this case because it's a load, and then source B, but then there are other potential cases, and then you do the addition, and then you supply it back to the PC, and then you need to enable the PC. So in this stage, these control signals need to be set. Okay. So store word, so you need to provide more data path until you exhaust everything in the ISA, of course, right? For store word, you need this data path on top of what we've had for the load. Because store is very similar to load. You just need to be able to do the store over here. Well, not over here, but this is the destination register. This is the source data that you need to read. You read it, you latch it, and you could latch it in either of those, right? Both of them are connected, so there needs to be a mux over there. But then you supply that to the write data port of the memory, and you need to enable that memWrite signal when you're executing in that state where you're doing the store word. Okay, R-type instructions, I think you get this point, right? You can go through this data path design. In fact, this is in the reading in Harris and Harris. But you need to provide data path elements to do the R-type instructions as well, because they don't use exactly the same registers, as you know, based on your study of the MIPS architecture. The destination register is different, and you need to choose the output coming from the ALU to write the data into the register file. That's why you need to add a mux, because sometimes you write to the register file what comes out of memory, right? That's the load path. But you need to provide the path for the R-type instruction as well. And the destination register is also different, because these have different encodings. So you need to set the control signals accordingly. And there's branch equal. As you can see, there's another path that you need to add. And this is PC enable. If the branch is taken, then you need to enable the PC over here. Otherwise, you don't enable the PC because you've incremented the PC by other means, right? And this is the target address calculation, which is different from the sign extended immediate, because you need to left shift it, because everything is 4-byte aligned, right? Instructions are 32 bytes in MIPS, 32 bits in MIPS. Okay, is this all clear? Yes? Or you will do the reading to make it more clear. So this is basically, we've completed the multi-cycle processor basically. This is at least with the instructions that we have. So you need to generate the control unit, of course, that's important, right? And the control unit basically takes in this case, it's combinational. Given the opcodes, you generate all the signals. And of course, there's a finite state machine over here, basically given the opcode and the state that you have. Now let's look at the finite state machine really quickly, and then we'll finish. Basically, you need to have a main controller. This is the fetch state. And these are the control signals asserted in that fetch state. Right? By the way, we've incremented the PC over here. This PC increment, PC plus 4, is done in the fetch state. You could do it in any state, really, in the instruction processing cycle, but we decided to do it over here. Decode state, no control signals enabled. Everything flows through and gets decoded in this combinational logic over here. That's the decoder, somewhere over here. And then memory address generation state. This happens if your opcode is load word or store word, you jump to this state, right? And then you set those signals. And then after that, you go to another state. Memread for a load word, memread, and then after that memread is done, the next clock cycle, you go to another state, memwrite back. We've just gone through this in the data path, but this is the state machine that requires a control. Basically, control logic needs to implement the state machine, right? If it's a store, you jump off this state to do a store, because this is memory address generation, right? You can share state across different instructions. If it's after decode, you figure out that it's an R-type instruction, the next state is execute, and you set some control signals. And then the next state after that is ALU write back. It's an   transition to the next state. And if it's a branch, you go to this state over here. Now we've got the complete FSM over here also. So I'm going to stop here, but we're going to do an analysis of this tomorrow, and we're going to go through microcoding and go into pipelining. Okay, see you tomorrow.